So the main reason why I didn't do a whole lot of videos in the last 3 weeks is that I finished my PhD thesis and I handed it in a few weeks ago. There were a lot of people who helped me along the way, for example by proofreading, and I just wanted to build them something as a little bit of a thank you note. Since I'm the hardware nut on our Department of Computer Science, I decided to build a little hardware device that you see here. So I'm going to show you what it can do, how it works, how I built it, and what errors I made during the design of this thing. So as you can see, this is the device. It has a 8x8 dot matrix display on front, and on the back side it has a DC to DC converter which converts the power from one AA cell to 5 volts, so it's a step-up converter. The only active components on the board are the microcontroller, which is an AVR ATmega8, and some EEPROM, which is a 24LC64, so 8 kilobytes of EEPROM. When the battery is plugged in, it displays a short message. For the ones that I'm giving out, it's a customized thank you note. And here it's just hello YouTube and just some animation. This is the front and back side of the PCB that I had manufactured at IT Studio. They deliver great quality for the price. One of these 5x5 centimeter boards is about $1. As you can see, all my components are on the top side of the board, so here. And on the bottom side there's the 8x8 dot matrix display. On the front and back side of the board I put a little doctor's hat in the silk print and a little German thank you message up here on the board. So my idea was to build it all and then have a programmer which I hook up here without soldering, so I can program the individual devices. If you've looked closely and you know what an AVR programmer looks like, you've already seen that I messed up once because I forgot to put a pin here. I forgot to route the reset pin down here, which means that for every board that I needed to program, I needed to solder a pin up here. Luckily, the reset is rather well exposed, so that wasn't too much of a problem, but it's still annoying. The drill diameter of these holes was chosen too wide by me, so when programming it kind of wiggles around and doesn't make for good contact. This is something I changed in a future revision. Then I put in 2 jumper pads here and there. One shorts the input to the DC to DC converter and the other one connects the output of the DC-DC to the board supply voltage. So the idea was that up here I could put in a switch or maybe measure current, which I didn't end up doing. And for programming, when supplying the voltage through these lines here, I left this one disconnected to not damage the DC to DC converter by supplying it with reverse voltage. This is the DC to DC converter that I used. It basically takes one AA input and it's used for USB charging. So my idea was to desolder the USB charging port, which I did do for all of the devices. And that turned out to be much more of a hassle than it should have. So in the future I would avoid using such a device where you have to do some desoldering at first before you can use it. And this is the MAX7219 module, which does the 8x8 multiplexing conveniently and has an SPI input that connects to the ATmega. In the silk print I've taken care to have the same symbols as on the board here, so that it's really easy to just place the components the correct way. One other change that would be smart if I did this again was to use bigger traces. So right here I have, I think it's 8mm trace, which is kind of flimsy. So they all held up perfectly, but they are a little bit too tiny for my comfort. So I'd use a 10mm or 16mm trace, especially here where it's perfectly permissible. This is the custom programming adapter that I built for it. So down here you have pins that hook into the board that you want to program. The yellow line needs to be soldered to the reset line because of my mess up. That ideally would also have been a pin here. Then it gets 5 volts DC via the black and red. And then it's already powered up and can be programmed via the ICSP up here. So this is just a standard ICSP and connects to a standard AVR programmer. And to load the pattern that is then displayed later on onto the EEPROM of the device, I use RS232. So here we have a FT232 and that connects to USB. So in the PC it's a serial console and I can just communicate via the AVR there and can program the EEPROM. So to show you how I build them, I will just build one now, and if you want to skip it, you can just click the link in the notation. Since I do my SMD work under the microscope, it's really difficult to film, but I hope that you get the gist of it. First I'll place the ATmega and then the EEPROM and then the other SMD components. I solder using a 0.2mm tip, using 0.5mm leaded solder wire and using 325 degrees C. At first I'll tack the ATmega in place. Then once it can't move again, it's easy to solder all the other leads. Now that this is done, we'll solder the EEPROM. There are 8 passive SMD components on this board, and I'll now put solder on one pad for each component. And be aware that I will always solder the one that is not connected to the ground plane, because that will take away a lot of heat. So for example, for these blocking caps here, I'll put solder on the inside, which is connected to a trace rather than the ground plane. Next I'll solder the 5 100 nanofarad capacitors. So now I've soldered one lead to each of the capacitors, and I'll now put in all of the 10K resistors, and then I'll solder the second lead to all passive SMD components. The first component we need to put in is the DC to DC converter. I'll first snap off the remaining piece of the PCB, which we don't need. Now, since these pins are all single, they won't have a lot of mechanical stability. This is why I use the following technique to get it done properly. So I first place all 4 pins inside, and then I can easily place the PCB in them. Then I solder them from the top, and for all non-SMD work I use a 0.5mm chisel. Now the pins are all in the correct location, and I can elevate the board a bit to solder it in from the bottom side as well. As you can see, again, the trick was to tack in one in place and then solder the others, and then finally come back to the first one. The dot matrix display doesn't have solderable pins as well, so we need to use the same approach here to fit them perfectly. And now that the daughter board fits in here perfectly, we can solder it in. So now I have put in 2 tacks and I can solder the rest. From the hardware side, now the board is ready for first test. So as I've shown you before, this is the programming station which I've clamped in a vise. This enables me to easily hook the board which I program in here, and that'll make a nice connection. But unfortunately I have to solder the reset pin first, because that's the one that I messed up on. So I'll do that quickly. Then I can just hook it in, power it up, and program it via ICSP. So my programming adapter is right here, and I can later on program the EEPROM via RS232. So here I'll give you a quick overview over the software. This is the firmware. It's pieced into many different modules, all of which are really short and really easy to understand. So the code is quite trivial, to be honest. For the I2C, I used a software implementation just because I was too lazy to figure out how the Mega8 does its I2C, and I already had that lying around, and it works. So then I have basically scripts that build the firmware, which is this thing, and then I have a script which does the first flash. So this initializes the fuses correctly for my project, flashes the firmware, and already loads the EEPROM content using the RS232 programming program. So how does the MAX7219 work in practice? Well, it's actually really easy. You just send it one command byte and then a value, and it has certain commands that it recognizes and 8 bytes that store the column data. And again, I use a software implementation just because this is a quick and dirty solution. So if you code this, you can do it nicer. I just wanted to, get it done. So you can see that the initialization routine is rather unusual in that it tries the same thing 3 times with pauses of 20 milliseconds in between. The reason for that is that when you plug in the battery, it doesn't always come up really clean, and I've had instances where the initialization failed, and this routine made it work in most of the cases. So for the RS232 loading, I've written a small Python script. Basically, I have a frame abstraction, and I have 4 commands that can be used. One to read out a frame, one to write a frame into EEPROM, and one to stop the firmware from accessing the I2C EEPROM during writing or reading. And it's really straightforward. The messages are always of the same format with only the command byte differing, and then it's all protected by CRC, so that, we're using the RC oscillator and 9600 baud, so it should work in most cases, but it doesn't always, and this ensures that we really catch all errors. Then there's some really trivial response handling, and basically just routines that use these frames and put them together to do something useful, like writing, reading, or verifying a whole EEPROM content. So this is shown down here. You can see that it tries to stop the device first so that the user space doesn't access the I2C anymore. And once that has succeeded, it'll try to write the EEPROM on the device, and it verifies it and determines which chunks of 32 bytes, so which EEPROM pages are bad, and it rewrites just these pages. At first I thought I needed this routine, but in the end it turned out that it was a bug that I coded in the firmware, and after I fixed the bug, this really isn't needed anymore. So a word about the command codes I used, because those are really weird numbers. I tried to find values which had the maximum Hamming distance to each other, so that the minimum amount of bits flipped to go from one command code to another is maximal. And for this I wrote this small script to figure out values that fulfill my criteria. I can run this just for fun now. And you can see that it pretty much instantly found 4 values which have a Hamming distance of 5 to each other. So every value to each other value is at least different in 5 bits. So that's really, really nice and handy to have such a feature. But it's, again, I guess, overkill, especially since everything is protected via CRC. So this shows the script that loads the firmware onto the devices. At first it slows down using the -B command the device, because initially the AVR comes up with a 1 MHz internal oscillator, and then it's reprogrammed to 4 MHz. That is needed because then I can quite safely use the 9600 baud without too much of an error. And you can also see that I choose the longest startup time, so 6 clock cycles plus 64 milliseconds. And I also activate the brownout detection and set it at 2.7 volts. And I activate the Watchdog timer from the very start. So these are all kind of paranoid things, because the battery and the way that it's inserted in the device really make for a very unclean startup of the device. So I want to do everything that I can that when the MCU does crash, it really recovers quickly. So I've set the Watchdog timer to 2 seconds timeout, which is the longest period for the Mega8. And that'll be sufficient, I think. So to actually create patterns, I wanted to simulate this on my host PC as well before I flash it down to the final device. And I actually even made a small editor for screens and some playback scripts that I can run to, see how it's going to look. And it's all emulated in the terminal, but it looks kind of nice. I'll show you. So this plays back a binary image that is also the EEPROM content. And you'll see that it basically emulates the display here in the terminal using large UTF characters. It looks really, really nice in my opinion. And this is the small editor that I also want to show you. You can call it with just a file name as a parameter. And then you can move your cursor around and, set buttons wherever you want them, and press return if you want to, take this frame, and then you can continue the animation and it'll save it to a file that you can then later on load. The way I generated my firmwares was using this MK EEPROM script. And as you can see, there is multiple classes that handle transitions from one screen to another. So there's a random transition, a rearrange transition, which rearranges pixels, and then fade via black or fade via white, and basically, it iterates over the pixels from bottom to top, left, right, top, bottom, and so on. And you can customize everything there. One is a noise transition where it, makes more and more pixels random, and then makes again for the target image less and less pixels random. So it kind of makes everything noisy, and then out of the noise appears the new screen. And then also there's animations. Here are some that, can be loaded from files that the editor generated. So these I generated by hand, and these I also generated by hand, but they are programmatic. So these are actually two classes that I wrote that make up a worm or a ring. And then what is done is basically it loads a CSV file where I stored, all the people that I want to thank and I want to give one of these devices to, and it just generates a little thank you text, and it displays an animation of all the letters with a transition that is also put in the CSV, and an animation at the end that is also in the CSV. Really easy. And then there's one important step. Just before it writes the binary image, it makes the animation Watchdog save. So the Watchdog is programmed to be at 2 seconds. So if I would have a screen that is longer than 2 seconds, the Watchdog would trigger and reset the device. So this basically ensures that it splits up all frames that are longer than 1.5 seconds into 2 or more consecutive frames of the same image. The constitution of the frames themselves is also really easy to understand. You have 9 bytes for each frame. The first byte signifies how long this frame shall be displayed, and then 8 bytes, which just are the raw data. And the way that the frame times are encoded is a kind of custom float implementation that I wrote for this. Probably also very much overkill, but I just wanted to do it properly. And in the end, it's the animation terminates by having FF as the time duration, which signals that it should loop at the beginning. So this is the float representation class that I mentioned, and basically it uses 6 bits of a mantissa and 2 bits of an exponent, and has the function by which it determines the actual value down here. And basically what it does is it's really simple. To determine which values for encoding fit closest, it just tries all values and just determines the error for each value and chooses the one with the least error. So this is really not very efficient, but since I don't have a whole bunch of frames and since it's only 256 values, that was really easy to do. And that's again the end of the video. Thank you so much for watching it. As I've mentioned, all the software is open source, so you can download it on GitHub, play around with it, do whatever you want. If you do something cool, shoot me a note. I really appreciate it and like to see what you guys do with it. Yeah, just have fun. Bye.